Alright, so 17. Power output of a fly that walks straight up a window pane. And, yeah. Alright, so the y is going to be one of our written y's. So, start with that. 17. So, what type of energy does the fly gain as it walks straight up the window pane?
Gravitational.
Gravitational potential. So I would start right away with that. The fly gains gravitational potential energy. The power is the rate the energy changes. And actually, I'm going to use the fact that, so to gain gravitational potential energy, what force does the fly have to do work against? Gravity, right? Otherwise known as the fly's weight, right? So the fly does work against, I'm going to say, gravity. I probably would put one more sentence in here, something like, the faster the fly works, the more power. So those are kind of my key ideas. All right. Oops. So I'm going to jump to my equation sheet, and I know that this one's about power. So I'm going to go down here to the bottom, and I have this big long equation about power, right? And I'm going to pick the form that talks about a force and the velocity or the speed that something moves at. And that's the one I'm going to use. So I'm going to use that power is whatever force is resisting my motion and the speed that I move at against that force. And all I really need to keep in mind mainly is that that force and that speed have to be in opposite directions but the same line for this to be a true relationship. Alright, so I also said that he's working against gravity, so I'd want to remember that the force of gravity on him is mg. So the power that is needed would be whatever force against him, the fly mg, and the speed that he's moving at. And now it's just simply substituting it, making sure I use the correct units. Because they want it in milliwatts. I'm probably going to find my answer in watts, and then I could convert it to milliwatts, right? Because that's an easy conversion. Or if I want to, I can just click into that box, get rid of the little m, and then have it input my answer in watts. The site is flexible enough to do that. That's probably personally what I would do. Then I have one less conversion. Yay, one less work. So, let's see, he has a mass of 1 gram and walks at 22.7 centimeters a second, so they're messing with me unit-wise a little bit, but I can do conversions in my head, so. So the power is just going to be that mass, which is that in kilograms. I'm assuming this takes place on the Earth, So I'm going to use the gravitational field strength on the surface of the Earth and then just convert my velocity to meters per second. And that will all work together to give me an answer when I'm finally done here in watts. And then I can convert it to milliwatts or something like that. Yeah? Good question. So, just to give you a reference rather than just telling you, is back here on our equation sheet, we look at the prefix kilogram, and that's times 10 to the third or 1,000. So that would tell me I'd move it over 3 decimal places. Ready to move on? All right, so number 19, where we got running up the flight of stairs just like you guys did in that lab in class. So I'm going to again do a written Y for this. And it's actually going to be very similar to 17's Y. So maybe there's a trend there. Not V, but U. Gain gravitational potential energy up the stairs. Power is the rate you gain energy. Yep. That shows me you understand everything. So, we're going to grab the power equation and use the form the change in energy over change in time. And, oops, and grab the potential energy gravitation relationship from our equation sheet also. Maybe this isn't grab on our and now it's just like last time, it's just really straightforward substitution. And you just grab your numbers from here. They want the answer in horsepower, so I'll have to do a conversion afterwards. In 3 minutes, 3 meters in 10 seconds, so good meters, seconds, and your mass is given this, and we're assuming this is on the surface of the Earth because I don't know that you've gone traveling. So now it's really just substituting in 82, 9.81 newtons per kilogram, 3 meters, 10 seconds. That's going to give you an answer in watts, just like before. And then you can take whatever answer you have in watts, multiply it by a clever number 1, which would be horsepower per watt, which I think is 1 horsepower to 746. Yeah. 746 watts. Okay. All right, so number 8, where we got the 2 motorcycles along a straight road, and it shows the position time graph and things like that. So, again, it's going to be a written Y. I would point out some facts like the motorcycles will pass when they are at the same place at the same time. Let's see, what else? The motorcycle that is accelerating will have a curved position graph, since, whoops, got a couple letters there. Since the slope, which is the velocity, is changing. Yeah, I'd say that's kind of the important factors here. So then on to the y here, and I'm going to, from my equation sheet, I'm going to look at the acceleration section here and apply that. So I'm going to start off with my main equation here. Where I end up is where I started, how I was moving when I started, and how long I moved, plus how I was accelerating and how long I moved. Right? My complete kinematics equation. Let's see. A you can do from if you understood the y. So B was positioned as two motorcycles, and motorcycle 2 passes motorcycle 1. Express your answer in 3 6 basically the appropriate units. So my unit's going to be meters. And so I know, let's see, I know about motorcycle 1, I know where it starts. I know its velocity. I know its acceleration. And I know how long it moves for. For motorcycle 2, I know where it starts. I know its starting velocity. I don't know its acceleration, but I do know how long it moves for. So I know a lot more about motorcycle 1 than I do motorcycle 2, but I know they'll be at the same position. So for part B, I'm going to use that same equation. And put in what I know. I don't know where they end up. I know where this one, so I'm doing this for motorcycle 1. I know motorcycle 1 starts at 50 meters. Now, does it ask how far it travels? Let's see. No, it just asks the position. So D is the position. You know, if I want to know how far they traveled, I figure out like the change in position, delta D, right? But they just want to know that. I know how fast it's moving at the beginning. For me, it's 6.5. And I know it moves for 10 seconds plus 1/2. It tells me it's not accelerating, so that's a 0. And then 10 seconds. All right. So I have 50 meters plus 65 meters. So I'm going to get 115 meters as that final position, or that position where they cross. Questions on that? All right. So on to part C. What is the acceleration of motorcycle 2? Well, I don't know that, but I know where it ends up now. I know it ends up at 115 meters. So I can use my same equation my same relationship. Except this time I'm doing it for motorcycle 1. So I know it ends up at 115 meters. It started at 0. Its initial velocity was 0. It moved for 10 seconds. 1/2, I don't know what A is, but I know it moved for 10 seconds. So I'm going to end up with A equals 115 meters over 50 seconds squared, which 2 point something, 2.2 2.3. Oh yeah, 15. 2.3 meters per second squared. Questions? Clarifications? And then, so on to part D. What is the speed of motorcycle 2 when it passes motorcycle 1? Alright, so part D. I have a couple of different approaches to this if I look at my equation sheet, because I have how the change in velocity relates to acceleration time, and how the change in velocity relates to acceleration displacement. The time one is a little easier math, right? Because it doesn't have those nasty squares. So that's what I'm going to pick to use. Doesn't matter which one you use, not at all. Whoops. Oops. Wow. So I don't know. Again, this is for motorcycle 2. I don't know what V final is. I know V initial was 0. My acceleration now I know is 2.3 meters per second squared. And my time, again, is 10 seconds. Oh, so look at that. 23 meters per second. Yay. Oh, I haven't been boxing my answers. Whoops. Any questions on part D? All right. All right, so we're going on to number 12 here. We've got a hot air balloon ascending at a rate of this when a passenger drops in. What does ascending mean? Going upwards. Good, because if you don't understand the vocab, you're going to struggle more. So, this is what, 12. I think I'm going to do a little diagram to help me just kind of keep track of it. So let's see, I've got the balloon, and it's got a velocity upwards, and it's some height, call it h, above the ground. It drops the camera. Now, from the balloon's frame of reference, the camera drops downwards, right? But from my frame of reference, the balloon's moving upwards, so the camera's moving upwards. So the camera has to go up until it stops, and then it can come down, right? So the camera's going to go up, and then eventually get down to the ground. That's our camera. From my frame of reference. So, also from my frame of reference, the camera is in free fall. Thus, accelerates down at the grav field strength. Right? Now the nice thing is, because I can worry about position and such, I don't really care what happens between the beginning and the end. I'm more interested in just the beginning and the end. So like the amount of time it takes to reach the ground, that's fine. That's throughout the whole motion. So I can look at the beginning and the end without worrying about whatever it does in the middle. And the same thing with the velocity it lands at. Again, I can look at the beginning, I can compare it to the end and talk about it. So that's really about all the... Now, you might add in here, especially if you didn't have the drawing, you might add something like the camera moves upwards, stops, and then moves downwards.
Also, what's the symbol between down and up?
Between what and what?
Down and up.
It's an at symbol. You'll find it in most emails. You know, like blah blah at. Yeah, it's an at. You making fun of me? Okay. Yeah, you're right. The handwriting sucks on it, but yeah, it's an at symbol. All right, so I know, shocking. I'm going back to our grand equation. And I know because it's in free fall that the acceleration is 9.81 negative. I'm going to call down negative. Is that okay with everyone? Yeah? Where do you, thinking back to our drawing, we're calling down negative, so that means up is positive. Where do you want to call 0? At the height of the balloon or at the ground? Or somewhere else? At the ground, okay. So we're going to call the ground at a height of 0. We're going to call up as positive. Okay. So the camera ends up at the ground. It starts at positive 27 meters. Right? I think that's right. Yeah. It's moving upwards when it starts. So that's going to be plus 7.8 meters per second. It moves for some amount of time. It's accelerating downwards, we said, 9.81 meters per second squared for that same amount of time squared. And just solve that. And that's just out through the algebra, right? Or the Wolfram, or the solver on your calculator, whatever. So that's part A. Any questions on A before we move to B? And yeah, I'm rushing a little bit to get this in. So B, it wants to know how fast it's moving just before it hits. If I look at my equation sheet, remember I've got the relationship between how fast things are going and time and how fast things are going and displacement. I'm going to actually use the displacement one. Because if I haven't checked my answer for part A. If I've got it right, I can do the top one with time. If I don't have it right, I'm going to screw up both parts. But if I do the displacement one, I'll only screw up A. That's actually smarter to do on the test, since you won't know if your part A is right or not. So, I don't know the final. I know the initial, 7.8 meters per second, plus 2 times negative 9.81 meters per second squared. My displacement, as with all changes, is final minus initial. So my ended up at 0. and it started at 27 meters, so 0 minus 27 meters. Again, now it's just all that's left is the fun math.